As we've seen, the electric potential due to a source charge Q depends only on the amount of charge that we have, Q, and the distance away from that charge for point charges. The electric field of this point charge Q is able to give another charge in it a potential energy. This potential energy, the ability of this source charge, the ability of this electric field to give another charge potential energy is what we call electric potential. Electric potential being the potential energy per unit charge. And in general, electric potential is defined as this: electric potential energy per unit charge, where Q prime is a second charge that would be placed in the electric field in order to measure its electric potential energy. Well, let's look at what happens when electric potential changes. So suppose that we have two charge configurations, that Q is equal to, we will say, 1 times 10 to the minus 6 coulombs. We will say Q prime is equal to minus 1 times 10 to the minus 6 coulombs. So these are equal and opposite charges. Q prime is opposite in sign to Q. And let's sketch some values, or let's add some values to the electric potential surfaces in this illustration. So let's just say hypothetically this line is a 100-volt line, and we will say this line corresponds to 75 volts. And then how about 50 volts? And then how about 35 volts? Let's say we place charge Q prime at a position right here on the 35 volt line. Let's ask the question, if Q prime starts from rest on the 35 volt line, and really that's an equipotential surface in three-dimensional space, how fast would it be moving when it reaches the 75 volt surface? Now remember, these equipotential surfaces are mathematical surfaces in space. They are not physical structures. And they are mathematical surfaces that describe a value of potential where everywhere on that surface, the potential is constant. So here we have our charge Q prime being a negative charge, that we know that Q prime will experience an attractive force to charge Q. So let's illustrate that attractive force in our picture. In the absence of other forces, Q prime will accelerate in the direction of the positive charge. Now, look at the equipotentials that Q prime will cross. It starts off at the 35 volt equipotential surface. It then goes to a higher equipotential surface at 50 volts, then goes to a higher equipotential surface when it reaches the 75 volt line. And the speed of Q prime will continue to increase as it accelerates towards our charge Q. So notice that this negative charge is accelerating from lower potential, 35 volts, to higher potential. And that's true of negative charges, that a negative charge will accelerate from low potential to higher potential. That is the nature of the relationship between potential surfaces, the electric field, and a source charge. So here, qualitatively, we know that negative charge is accelerating from low potential to high potential. Let's see if we could determine how fast it's moving when it reaches the 75 volt line. To do that, we again recognize that electric potential, due to a source charge Q, is defined as the change of electric potential energy between two charges, Q and Q prime, over the charge that we place in the electric field of the source charge. Well, in this situation, we have charge Q prime changing speed. It starts from rest and it accelerates to some speed. Our goal is to find that speed. Now, I remember from conservation of energy that in the absence of external forces, the change of kinetic energy in a system plus the change of potential energy of that system is equal to 0 in the absence of external non-conservative forces, which means those non-conservative forces would do 0 work. So I'm going to use this because I know that our charge initially starts from rest. And I'll just go ahead and indicate that the final velocity is unknown. We probably need to know the mass of the charge for this problem. So let's just say that this charge has a mass of 6.0 times 10 to the minus 10 kilograms. These are just arbitrary numbers that I just thought of. I haven't worked this out yet, so I'm not sure what the answer is going to be numerically, but the logic will be good. So now that we know the initial speed of our charge Q prime, and we know the mass, so let me signify this with the mass of Q prime. Let's see if we could figure out how fast Q prime will be moving. Now for this problem, let's hold fixed charge Q. So we are saying that charge Q is not going to be moving in space. It's going to be held stationary. So let's look at this then. This would become the change of kinetic energy for charge Q plus the change of kinetic energy for charge Q prime, because this is our system, plus the change of potential energy for the Q prime system is equal to 0. I have said that we are holding charge Q fixed in space, so there will be no change in its kinetic energy because it's not changing speed. This leaves us with the change of kinetic energy for charge Q prime, and that is its final kinetic energy. Then this is plus the change in its potential energy. Since Q prime starts from rest with 0 speed, it has zero initial kinetic energy. Substituting in the formula for kinetic energy, we have the kinetic energy of Q prime being equal to 1/2 times its mass times its final speed squared, and that is added to the change of the potential energy of this system. Let's isolate the speed by moving the potential energy to the other side. And let's multiply by 2 over the mass of charge Q. And now let's recognize something. Since potential energy, or since electric potential rather, is defined as electric potential energy per unit charge, the change in electric potential is equal to the change in electric potential energy per unit charge. So this is a useful result, that changes in electric potential energy lead to changes in electric potential. We don't have the change of potential energy for this problem, but we do have the change in electric potential. When you look at our sketch, we're going from an initial potential of 35 volts to a final potential of 75 volts. Since we have the change of potential between the 2 points that we are interested in for our charge, we could express then the change of electric potential energy is equal to the product of the charge placed in our electric field times the change of electric potential between the 2 points. Substituting this into our expression, we have minus 2 over the mass of charge Q prime times the charge Q prime placed in the field times the change of electric potential between those 2 points. This means that the speed squared is equal to minus 2 over the mass of charge Q prime times charge Q prime times the final potential that it finds itself in minus the initial potential that it finds itself in. Let's identify those. The final potential is 75 volts. The initial potential is 35 volts. So we now know all the quantities we need. So let's go ahead and evaluate this. The speed is equal to minus 2 over the mass of our charge times our charge Q prime times the difference in electric potential between the 2 points. This is all under the square root. Let's plug in numbers for this. This is minus 2. The mass of charge Q prime is 6.0 times 10 to the minus 10 kilograms. The magnitude of the charge for Q prime, let's look at what we said for that. We said Q prime is minus 1 microcoulombs. So this is minus 1 times 10 to the minus 6 coulombs. And this is times the difference in potential. The final potential is 75 volts. The initial potential was 35 volts. So notice the negative times a negative underneath the square root ends up being a positive. And when I plug this into my calculator, I get that the final speed of the particle to one significant figure is 400 meters per second. This is extremely fast. By the time the charge reaches the 75-volt equipotential surface, it's traveling at a speed of over 400 meters per second. That's about a quarter mile per second. Now, notice in this problem that we didn't know the distances between these two equipotential surfaces. We didn't know the distance from the source charge to the 75-volt surface, nor did we know the distance from the source charge to the 35-volt surface. But that doesn't matter, because the fact that electric potential is based off of potential energy, and potential energy is an energy of relative position, by saying something has 35 volts of electric potential at a certain distance and 75 volts of electric potential at a certain distance, and knowing the difference in those electric potentials already incorporates the distance in there. So what matters is the change of electric potential, regardless of how great the distance is, whether the distance between those two equal potential surfaces was 1 meter or 1 kilometer. The change of energy remains the same, which means regardless of that distance, the speed that our particle will acquire when it reaches the 75-volt line will still be 400 meters per second.